Okay, on to part C of the interference of light. I'm going to look at transmission gratings now. So transmission gratings, there's a lot of similarities between that and the double slit, the two slit interference. In a sense, the transmission grating is probably in some ways a little bit simpler though, hopefully. So what does it look like in the lab? Well, we have here a picture just of me holding a transmission diffraction grating. This one has 600 lines per millimetre. It's almost rubbed off. Sometimes kids can get a bit confused on this. 600 lines per mil means that the distance between each line is 1 on 600, if that's in millimetres. And then obviously if we need it in metres for standard units, we've got to divide that by 1,000. So in this case here, the distance between those slits would be 1.7 times 10 to the minus 6 metres, or 1.7 micrometres. Micrometres. A millimetre is 1,000th of a millimetre. A micrometre is 1,000,000th of a millimetre. So when we look at this, at least with coherent light, using a laser again here, if we shine the coherent light through, and we're going to look at what happens when we shine white light as well through this later, but if we shine coherent light through here, we get this diffraction pattern set up. So mainly you notice that the bands are much further apart, and that's basically because D is much smaller, so delta Y is inversely proportional to D if you go back to that formula we had on the last slide. So as D gets smaller, these get further apart. You'll also notice, and we'll talk about this some more in a sec, that you basically have very narrow bands of high intensity, and you've got these large regions in between them of almost zero or little intensity. And we'll explain why we get that pattern. Whereas with the two-slit experiment, it was pretty much half and half, half and half. Half dark, half light, half dark, half light. But now we can see large areas of nothing with some very bright bands in between. Okay, so let's get into the details of the proof. Well, the details of explaining this more so. So we've already said a transmission grating consists of many thin, equally spaced parallel slits. The interference of light from a grating in a pattern, the pattern basically consists of very narrow, intense maxima separated by regions of negligible intensity. I showed that on the previous slide, and there's this little picture down here showing that as well. So why do we get this pattern? Firstly, we've got to realise that light can overlap. The light coming in here might be, a few mil across. These slits are only microns across, so the light is going to basically be covering hundreds to thousands of slits on this slide. Now, the first part is, why is the angle so much greater here than it was with two slit, where there was only a very small angle between that first and second bright band? Well, that's because D, in this case, is very small. The distance between the slits is much smaller than it was for the double slit. And from the equation over here, d sine theta equals m lambda, sine theta is inversely proportional to D. So as D gets smaller, the angle of reinforcement gets larger. So we see the bigger angles because of that sine theta is inversely proportional to 1 on D. Now, why do we get all these regions of negligible intensity and just these very narrow bright bands? And my explanation here, my diagram are not quite perfect, but I think you'll be able to work it out. So, if you think here, obviously if the path difference between the light coming through here and here, so that path difference here, is half a wavelength, this one will destructively interfere with this one and cancel out. So we'd see no intensity, because then this one would interfere with this one, and so on. If it was only a quarter of a wavelength, this one here would only be a quarter of a wavelength out of phase with this, so those two wouldn't destructively interfere. But the path difference between here and here, so that's indicated with this triangle here, that's the path difference for the two slits. If that was a quarter, that'd be a half, so this would be a half and this would be a half, and those two would destructively interfere and cancel each other out. If it was what to say, a quarter, even if it was an eighth of a wavelength out of phase, okay, 1/8 between this and this one, they won't distractively interfere, but then it would be 2/8 with this one, so that's only a quarter, so they would cancel each other out a little bit, but not completely. 3/8 for this one, 4/8 for this one, 4/8 is a half, so this one would cancel out with this one, because the path difference here, even though it was only an eighth of a wavelength, 1, 2, 3, 4/8 equals a half, that would cancel out with that one. So that's why we get those large regions of negligible intensity. We can only get constructive interference, we can only get a bright band at an angle where the diffracted light is exactly in phase. So where the light between this one and this one and this one and this one are exactly in phase. If they're only a little bit out of phase, there'll be one somewhere down here that'll cancel out with this one here. So I think, yeah, that describes the pattern. So the proof here is fairly simple, and I won't really even go through it in that much detail. We can see there's our path difference. This angle here is equal to theta. Therefore, this angle here is equal to theta as well. That is D, path difference, sine theta. Well, the line above this would say sine theta equals opposite, which is path difference, over hypotenuse, which is D, path difference equals D sine theta when we rearrange that. So that's really the proof there. It's a very obvious one, particularly if you've understood the previous one. So hopefully we can derive, hopefully we can explain, give a qualitative explanation of the negligible intensity between maxima. So that was this whole thing here. Hopefully we can solve problems without a formula with a bit of practice. Sketch a graph of the intensity distribution of the maxima produced by a grating from a monochromatic light. Pretty simple. If we have intensity here and we have our pattern going across here, low intensity, we get a little spike there, then 0, low, 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 bit bigger spike, come across, biggest one in the middle, then back to not much at all, little one there, same as the size as the one on the other side, and then there is a little one there, like that. So that's what the intensity, would look like. Bright, nothing, bit brighter, nothing, brightest, highest, nothing, and so on. We can actually, finally, this one, determine the distance between the slits in the grating, determine from the distance between the slits in the grating the maximum number of orders for a given diffraction grating. So what we're talking about really here is, if you're shining your laser at a screen like this, the maximum angle you're going to be able to, if you can imagine these being your bright spots, the maximum angle that you'll be able to see anything at as theta equals 90. So at theta equals 90, well, put that into length, m lambda equals d sine theta. So m is going to be, if you like, the maximum order, so that's 0, 1, 2, and so on, will equal d sine 90, which is 1 over the wavelength, so that there will equal 1. That'll tell you the maximum value of m. Now remember, the number of bands that you'll see will be equal to 2m, because you'll see one on this side and one on this side, and you'll see 2 on this side and 2 on this side, and so on. So there'll be 2 plus you'll see the 0 one in the middle. So the bands that you see here will be equal to 2m plus 1 when you put theta equals 90, therefore sine theta equals 1 into that equation. You'll do those in the book. I think you'll work them out. They're not too difficult. You can also describe, well, you should be able to also work out how, and we'll do this in the lab for those who I see, the wavelength of a light source by using this pattern. Because if we can work out the angle, we can basically know, if we know the angle, we know theta, work out sine theta. If we know the distance between the slits, for example, we showed in the previous slide how to work out the distance between the slits, and if we know whether it's the 0 or the 1, etc., we can then plug it into that formula and work out the wavelength of the light source. Hopefully you'll see, and we'll do that, and it's not too challenging. Okay. We've got some more to talk about still with transmission gratings, particularly with white light. We'll get onto that now. Okay, so finally, we want to talk about what happens when we put white light through a grating. And this really leads into the concept of spectroscopy, which is the idea of analysing the wavelengths or the colours that make up a light source. So what we have here, for example, is a continuous spectrum of white light. So white light is made up of all the colours of our rainbow, if you like, Roy Jabiv, red, orange, etc. So if we look at white light through a spectroscope, which is built, which contains a transmission grating, this is the sort of pattern we'll see. In the lab, we might have looked at the fluorescent light globes through these and seen this sort of pattern here, which is basically the gases that make up those fluoro. That's the lines that they're emitting. We're going to come back later in the year and talk about emission and absorption spectroscopy in the final topic when we talk about the structure of the hydrogen atom, so I don't want to worry about that too much now. But I guess I do need to point out that the angle of reinforcement is proportional to the wavelength, therefore different colours, which have different wavelengths, reinforce at different angles. So this idea that sine theta is proportional to wavelength, so different colours will reinforce at different angles, and by looking at different angles we can see whether that wavelength or that colour is present in a light source or not present in a light source. So they might do that to analyse an atom, they might do that to analyse a distant star and see which gases are in the atmosphere and have actually absorbed some of the white light that star's emitting. So gases that absorb it will take it out, and that gives us clues as to what distant stars are made of. So how do we achieve this in the lab? Well, we use a bit of equipment down here called a spectroscope. Shine, in this case, white light down this tube through a transmission grating, and it goes into this eyepiece. This eyepiece can be moved around at various angles. To make this work, down here we have a little single slit like such. That's a photo of a close-up, just to make the light that comes through there coherent. Then, obviously, if we look straight through here at an angle of 0 degrees, well, path difference will be 0 for all light, so we'll see this very white, bright white brown where all the colours reinforce. But then as we increase our angle around here, we will see, and this isn't a great photo, but you can start to see the sort of rainbow type effect in there, and that's telling us what colours are present in this light here that's being produced. So that should look something like one of these spectra up here. So that's, if you like, how we go about working out all the colours that make up a light source. Because D is really small, we get big angular variations for different wavelengths, so that means the transmission grating is excellent for that because it's got a very small distance between the slits D, and because of that whole light overlaps several slits, and even if they're only a small amount out of phase, they can overlap each with one down that slit and cancel each other out, so you only see constructive interference when it's exactly in phase, so you don't get sort of interference and blurring out of your light. So that very sharp maxima is also really important.